चलो, today we are going to continue the class of sigmatropic shift. Okay, earlier we have studied the definition of sigmatropic shift and then the naming of sigmatropic. How does it we name it like 1-3 shift, 1-5 shift, 1-7 shift. इस तरह से जो the different class of sigmatropic shifts are already discussed in the previous class. Today in our class we are going to learn about the selection rule. That is, which type of sigmatropic reactions are photochemically allowed and which type of reactions are thermally allowed. To know that selection rule, to understand that selection rule, we need to have some knowledge of the representation of sigmatropic reactions in terms of lobes, in terms of molecular orbitals. Okay? So for drawing molecular orbitals, I have taken an example of Lorentz system. The first basic reaction which I have taught you in previous class, that is this. G group is migrating from one position to three position, already discussed. So this one from one position to three position, and the product form is this through 1-3 shift. Therefore, this type of sigmatropic reactions, from the knowledge of our previous class, we can say this is 1-3 sigmatropic shift. In this 1-3 sigmatropic shift, if we have to study this in terms of mechanism, so what is suggested is this sigmatropic reaction takes place through homolytic bond fission. Homolytic bond fission means generation of free radicals. Generation of free radical, how does it take place? The 4n system, that is 2 pi electrons here and 2 sigma electrons here, they all contribute to have a 4n system. In this, these sigma electrons are homolytically divided into two parts. That is, this G gets 1 electron and this CH2 gets 1 electron to produce this allyl free radical. This is an allyl free radical. This allyl free radical is a resonance system, right? You can migrate this like this, and one electron from this bond will come to this, and the other electron will go here, so that we have a double bond over here and a free radical generation at the destination carbon. This destination carbon can have that free radical generated in the first step to have this. But as we know, the pericyclic reactions go via cyclic transition state. So the cyclic transition states look like this. When this free radical is resonating from position number 1 to position number 3, this G can have the attraction from both the sides to have two, and so the representation of the cyclic transition state is like this. Then after some time, this will generate a new product. This new product is now we are going to study about the how does this takes place in view of molecular orbitals. So in the next part of the video, I am going to draw the molecular orbitals of this allyl free radical. So allyl free radical, in allyl free radical we know we have 3 carbon atoms. So therefore we can have psi 1, psi 2, psi 3. Psi 3 up to psi 3 is, so we have to draw. Psi 4, psi 5 भी होती हैं, hypothetically they exist. Let it be कि वो हमारे लिए useful है कि नहीं है, लेकिन we have to draw at least psi 1, psi 2 and psi 3. So for this allyl free radical, let's assume that we have psi 1, then we have psi 2, then we have psi 3. From the previous knowledge, we can calculate the number of nodes beta. The number of nodes is n minus 1. Okay, so this will have 0 node, 1 minus 1. This will have 1 node, 2 minus 1. This will have 2 nodes, 3 minus 1. So this is how we calculate the nodes, number of nodes. Then to draw these lobes, we have to draw 3 lobes. 1, 2, 3. Because of the presence of 3 carbon atoms, we have to draw 3 p orbitals. These lobes are the p orbitals participating in that pi framework what I have discussed in previous class. So these 3 lobes, then from our previous knowledge, we can say if this is an odd, this number is an odd, then the terminal lobe will have same sign. Okay? If this is an even, then terminal lobe will have different sign. This is an even number, but terminal lobe will have different sign. Clear? Clear? So this is obvious. This in this, again, if we draw 3 lobes. Because of this is odd, the terminal lobe will have same sign. Clear? So it's because we have this we have learned the condition for drawing these lobes, the basic first lecture. So from the previous knowledge we have learned up to this part. This is plus, then this will be minus. This is plus, then this will be minus. What about the middle one? What about the middle one? Since it has 0 nodes. 0 nodes matlab all the interactions are of bonding type. There is no node, therefore this will have plus and minus. Bonding interaction, bonding interaction. There is no plus minus condition. Clear? This much is clear. In the second one, we have one node. One node. One node has to be, and that node has to give a symmetrical picture. So for that, since this is even plus minus opposite, even means opposite, so this is minus and this is plus, and to put one node which gives a symmetrical figure, there is no other option than to have the node at this position. The carbon number 2 will get a nodal point. You can, I don't know it's right or not, but I can explain. Yeah, it should be like, since in the free radical, in the resonance of the free radical, you get an electron over here, you get an electron over here, but you never get an electron in the middle one. Therefore, this will act as a node. Okay? God knows if this explanation is right or not, but yes, to remember this, I can use this explanation also. Then inside there are 2 nodes. 2 nodes means symmetrical condition. So without anything, we can have 2 nodes over here. This is plus, this is minus, this is plus, this is minus, and this node will always come with an anti-bond interaction. Therefore, this will be minus. Anti-bond relation, therefore this will be minus. So this is the basic thing from the knowledge of this, that this is an odd number, therefore terminal nodes will have same sign. This is an even number, terminal node will have different sign. Then with the help of the number of nodes, we can say this C2 carbon will act as the center of this center will act as a nodal point. Therefore, then again we have to have the electronic configuration. We need to know the electronic configuration. Electronic configuration we have to fill 4 electrons. There are in an analytic system 1 electron is gone with this G. So there are only 3. So if for filling the electrons we have to fill 3 electrons. So 3 electron is like in thermal condition normal filling 2 electrons. The remaining 1 electron will go here. Okay. Then we have to point out what is HOMO and what is LUMO. Highest occupied molecular orbital, highest occupied molecular orbital is HOMO, and this is LUMO, unoccupied molecular orbital. And in photochemical conditions, what we do is we excite this to a next higher energy level. Therefore, if psi 5 exists, psi 4 exists, if psi 4 exists, and it exists, hypothetically all the higher energy levels will exist. So this electron will jump into this position. So this is now HOMO and this will act as LUMO. So in photochemical conditions, in thermal conditions, 3 electrons are filled normally. In photochemical conditions, as I have earlier told, 1 electron from the HOMO will jump into LUMO. This gives the actual representation of the molecular orbitals in allylic system. This is for allylic radical. Draw. So now we are going to draw the molecular orbital picture of a system, conjugated allylic system, in which we have shown 1,5 shape. For 1,5 shape, these electrons which are directly attached with the origin carbon, with the G group from the origin carbon is going to migrate to the destination carbon, the 5th carbon. Therefore, we are naming it as 1,5 sigmatropic shape. In this 1,5 sigmatropic shape, if this again occurs through a homolytic bond fission. Homolytic bond fission means generation of free radical. At this point a free radical will be generated. This free radical can resonate to have a free radical over here. Then this free radical can resonate to have this bond shifting to this position. This bond shifting to this position. This free radical shape like the double bond will occur here. Then this double bond will move over here, and then again the free radical will generate over this place. So this type of, again I will show the cyclic transition state in which this G free radical generated over here will have attraction of all the positions from first, that is from origin, to the last, that is fifth. This interaction to have a cyclic transition state, as I have explained in 1P type of shape. Now we have to draw, since there are 5 carbon atoms, we have to draw the lobes taking part in the p orbitals which are taking part in the reaction in this type of 1,5 shape. These are psi1, psi2, psi3, psi4 and psi5. To draw from the basics, like we need to have the knowledge of nodes. Node is very simple, that is n minus 1, 0 node, 1 node, 2 node, that is 3 minus 1 is 2, 4 minus 1 is 3, 5 minus 1 is 4. So we have calculated the total number of nodes. Then simply draw 5 lobes. Already it has been drawn. Let's think that we have started. So draw 5 lobes. This is an odd number. Odd number indicates the terminal position have same sign. Terminal position will have same sign. This plus and this plus. So the 2 plus at the terminal position. Now since there are no nodes, so therefore there will be a bonding condition in all the time. Therefore plus will have plus. A bonding condition, this plus should have a plus in bonding condition. So all the lobes above will have positive sign. In side 2 we are going to have one node, and in side 2 this 2 indicates that the terminal position will have different sign. Even matlab different sign. So this different sign gives plus and minus over here. So forget about these positions. I will make it again for you. This will have different sign, so therefore plus and minus, corresponding minus and then plus over here. Okay, then since there are one node, and then one node must be symmetrical in nature, therefore the third carbon will be a nodal point in case of side 2. This plus and this low and this low will have a bonding condition. There is no node, therefore automatically it will have plus and minus sign. This will have a bonding condition, since it is minus, therefore a minus over here and then a bonding condition. In a similar fashion, psi 3 is odd. Odd means same sign on terminal position, same sign with the terminal position with the corresponding signs, negative signs over the lower lobe. Then we have 2 nodes for symmetrical reasons. 2 nodes will be like a node between 1 and 3 and a node between 3 and 5 will give a symmetrical position of the nodes. Therefore, now since this is positive and this is negative, with this is positive and a node, then a terminal lobe. Therefore, after the node there should be a different sign. So this is plus and we have to have a negative sign over here, so that it automatically fills the condition of anti-bonding conditions over here with a node over here. In the similar fashion, we have drawn all the nodes, like in fourth, like in fifth, psi 5, we have 4 nodes and 4 nodes. This is 5. The terminal position will have same condition. 4 nodes in 4 symmetrical regions. So without consuming any carbon point, we can have 4 different nodes placed in between the lobes. And since all these are having a node in between, therefore plus minus will have it. This is again having a node, minus plus will have it. Plus minus, minus plus. So this is the simpler way in which we can draw any system, the nodes and the molecular orbital picture of any type of systems. Now to fill the electrons, what I have said is, now we are having number of electrons is 2 electrons from this pi electron, 2 electrons from this pi bond, and 1 from this allylic, from this free radical point. Therefore, total we have to fill 5 electrons. The 5 electrons in thermal conditions will be filled as usual, normal, that is 2 from the lowest energy available, then 2 to the psi 2, then remaining 1 in the psi 3. This psi 3 is now, psi 3 will act as a HOMO in thermal conditions, and psi 4 is LUMO. We have to focus on HOMO since on all the reactions, in pericyclic reactions, the HOMO is the orbital which is going to participate in the bond formation, in the product formation. Now in photochemical conditions, one electron from the HOMO will excite to the higher energy level. Therefore, the electron from the psi 3 will go to psi 4. So in photochemical condition, we will use this psi 4 for explaining the selection rule, which I will discuss in the next part of the video. And this psi 5 will become LUMO. Basically, we have from this, we now can say when we are going to discuss the selection rule in case of sigmatropic reactions, so in 4n plus 2 systems, psi 3 will be used in thermal conditions and psi 4 will be used in photochemical